Hey everyone, welcome back to Cosmic Wonders. Today we're diving into one of the biggest questions ever. How did our universe start from nothing? Yeah, you heard that right, nothing. It's a mind-blowing concept, so let's break it down and explore the mysteries of our cosmic origins. Our journey begins with the Big Bang, the colossal explosion that marked the birth of our universe around 13.8 billion years ago. This event set everything into motion, creating the very fabric of space and time. In the first few moments after the Big Bang, the universe expanded at an unimaginable rate, a period known as cosmic inflation. This rapid expansion laid the groundwork for the formation of all matter and energy. As the universe cooled, subatomic particles began to form, eventually giving rise to protons, neutrons, and electrons. These particles combined to create the first simple atoms, primarily hydrogen and helium. Over millions of years, these atoms clumped together under the force of gravity, forming the first stars. These stars were the cosmic furnaces where heavier elements were forged through nuclear fusion. Stars grouped together to form star clusters and galaxies, vast collections of stars, gas, and dust bound by gravity. Our own Milky Way galaxy is just one of billions in the observable universe. Galaxies themselves are dynamic entities, often colliding and merging to form new structures. These cosmic interactions play a crucial role in the evolution of the universe. On a grander scale, galaxies are arranged in a vast cosmic web, with filaments of dark matter and gas connecting them across the universe. This intricate structure is a testament to the complexity and beauty of our cosmos. By studying the light from distant stars and galaxies, astronomers can peer back in time, uncovering the history of the universe and its ongoing evolution. So, as we explore the cosmic origins, we not only learn about the past, but also gain insights into the future of our universe. Stay tuned as we delve deeper into these fascinating topics in the upcoming chapters. First, let's rewind about 13.8 billion years ago. There was no space, no time, no matter, just nothingness. And then in a fraction of a second, everything changed. This moment is what scientists call the Big Bang. The Big Bang theory is the leading explanation about how the universe began. At its simplest, it talks about the universe as we know it, starting with a small singularity, then inflating over the next 13.8 billion years to the cosmos that we know today. One of the key pieces of evidence supporting the Big Bang theory is the cosmic microwave background radiation. This is the afterglow of the Big Bang, a faint cosmic background radiation filling the universe and detectable in every direction. Another crucial piece of evidence comes from the observation of distant galaxies. Thanks to the Hubble Space Telescope, we know that galaxies are moving away from us in all directions, suggesting that the universe is still expanding. This expansion is evidenced by the redshift of light from these galaxies. The further away a galaxy is, the more its light is shifted to the red end of the spectrum, indicating it is moving away from us at a faster rate. Additionally, the Big Bang theory predicts the abundance of light elements such as hydrogen, helium, and lithium in the universe. Observations of these elements in the oldest stars and gas clouds match the predicted amounts, further supporting the theory. The large-scale structure of the universe also aligns with the Big Bang theory. The distribution of galaxies and galaxy clusters throughout the cosmos follows patterns that simulations based on the Big Bang model predict. The implications of the Big Bang theory are profound. It suggests that the universe had a beginning and has been evolving ever since. It also leads to questions about the nature of dark matter and dark energy, which make up most of the universe's mass energy content. Understanding the Big Bang helps us predict the future of the universe. Will it continue to expand forever, or will it eventually collapse back on itself? These are questions that scientists are still trying to answer. The Big Bang theory is not just a theory. It's a framework that helps scientists understand the past, present, and future of the universe. It is a cornerstone of modern cosmology, guiding research and discovery. From the formation of the first stars and galaxies to the complex structures we see today, the Big Bang theory provides a comprehensive explanation of the universe's evolution. So the next time you look up at the night sky, remember that it all started with a bang, a Big Bang that set everything in motion, leading to the universe we inhabit today. But wait, how can something come from nothing? That's the mind-boggling part. According to quantum mechanics, particles can pop in and out of existence. It's like the universe borrowed energy from, well, itself. Quantum mechanics, the branch of physics that deals with the behavior of particles on the smallest scales, provides a framework for understanding this phenomenon. At the heart of quantum mechanics is the concept of quantum fluctuations. These fluctuations are temporary changes in the amount of energy in a point in space, leading to the creation and annihilation of particles. Imagine a vacuum, seemingly empty but teeming with activity at the quantum level. This is where Heisenberg's uncertainty principle comes into play. It states that we cannot simultaneously know the exact position and momentum of a particle. This inherent uncertainty allows for the spontaneous creation of particles. These particles, often referred to as virtual particles, exist for incredibly short periods before annihilating each other. Yet their brief existence has profound implications for the universe. The early universe was a hotbed of quantum activity. These quantum fluctuations could have provided the seeds for the large-scale structures we observe today, such as galaxies and clusters of galaxies. Evidence of these early quantum fluctuations can be seen in the cosmic microwave background radiation, the afterglow of the Big Bang. Tiny variations in this radiation map out the density fluctuations in the early universe. Over billions of years, these small fluctuations grew under the influence of gravity, leading to the formation of stars, galaxies, and ultimately, the universe as we know it. Quantum field theory, which combines quantum mechanics with special relativity, further explains how particles interact and how forces like electromagnetism and gravity operate at the quantum level. One of the most significant discoveries in quantum mechanics is the Higgs field, which gives particles their mass. Without it, the universe would be a very different place. In essence, quantum mechanics not only explains the behavior of the smallest particles, but also provides insights into the very fabric of the universe. From the tiniest quantum fluctuations to the vast cosmic structures, it all starts with quantum mechanics. Imagine the universe as a giant balloon. At the Big Bang, it started inflating rapidly. This expansion is still happening today, which is why galaxies are moving away from us. The Big Bang, occurring approximately 13.8 billion years ago, marked the beginning of this expansion. Initially, the universe was an incredibly hot and dense point, often referred to as a singularity. In the first few moments after the Big Bang, the universe expanded exponentially in a period known as cosmic inflation. This rapid expansion set the stage for the formation of matter and the large-scale structure of the cosmos. As the universe continued to expand, it cooled down, allowing particles to combine and form atoms. This led to the creation of the first elements, primarily hydrogen and helium. Over billions of years, these elements coalesced under the force of gravity to form stars and galaxies. The universe's expansion has not been uniform. It has been influenced by various factors, including dark matter and dark energy. Dark matter, which makes up about 27% of the universe, exerts gravitational forces that affect the motion of galaxies and galaxy clusters. However, it does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects. On the other hand, dark energy, which constitutes roughly 68% of the universe, is a mysterious force driving the accelerated expansion of the universe. Unlike dark matter, dark energy is thought to be uniformly distributed throughout space. The discovery of dark energy in the late 20th century was a groundbreaking moment in cosmology. Observations of distant supernovae revealed that the universe's expansion is speeding up, contrary to the expectation that it would slow down due to gravitational attraction. This accelerated expansion suggests that dark energy is a fundamental property of space itself, often associated with the cosmological constant, a term introduced by Albert Einstein in his equations of general relativity. The exact nature of dark energy remains one of the biggest mysteries in modern physics. Researchers are exploring various theories, including the possibility that it could be a new form of energy field or a modification of our understanding of gravity. As we continue to study the universe's expansion, we gain deeper insights into its origins, structure, and ultimate fate. The interplay between dark matter, dark energy, and ordinary matter shapes the cosmos we observe today. Understanding the expansion of the universe not only helps us comprehend our cosmic history, but also provides clues about the future. Will the universe continue to expand forever, or will it eventually collapse back on itself? These are questions that drive the quest for knowledge in cosmology. The expansion of the universe is a testament to the dynamic and ever-changing nature of the cosmos. From the explosive birth of the Big Bang to the mysterious forces of dark energy, the story of the universe's expansion is a journey through time and space. As we unravel the mysteries of the universe, we come closer to understanding our place within it. The expansion of the universe is not just a scientific concept. It's a profound narrative that connects us to the very fabric of existence. And so the universe continues to expand, carrying with it the secrets of its past and the potential of its future. Now here's the crazy part. The total energy of the universe is zero. Sounds weird, right? Think of it like this. Positive energy, which is matter, and negative energy, which is gravity, cancel each other out. So in a way, the universe is a perfect balance of nothing. But wait, there's more to this story. The universe isn't just made up of matter and gravity. There's also dark matter and dark energy. Dark matter is a mysterious substance that doesn't emit light or energy, making it invisible and detectable only through its gravitational effects. It acts like a cosmic glue, holding galaxies together and accounting for about 27% of the universe's mass energy content. On the other hand, dark energy is an even more enigmatic force, responsible for the accelerated expansion of the universe. It makes up roughly 68% of the universe, pushing galaxies apart and driving the expansion at an ever-increasing rate. So when we talk about the energy balance in the universe, we must consider not just matter and gravity, but also dark matter and dark energy. This intricate balance of forces and energies creates the dynamic and ever-evolving cosmos we observe today. Scientists are still trying to understand the exact nature of dark matter and dark energy, but their influence on the universe is undeniable. Through simulations and observations, researchers are piecing together the puzzle of how these components interact and shape the universe. The energy balance in the universe is a delicate dance, a cosmic equilibrium that has profound implications for the fate of everything we know. As we continue to explore and understand this balance, we uncover more about the fundamental nature of reality itself. The universe, in its vastness and complexity, remains a perfect balance of forces, energies, and mysteries waiting to be unraveled. But how did this initial spark happen? Scientists have a few theories. One is called quantum fluctuation. It's like the universe got a little nudge from these tiny fluctuations, causing it to explode into existence. Another prominent theory is the Big Bang theory. This theory suggests that the universe began as a singular, incredibly dense and hot point, which then expanded rapidly. This expansion continues even today, leading to the vast cosmos we observe. However, not all scientists agree with the Big Bang theory. The steady state theory, for instance, proposes that the universe has always existed in a constant state. According to this theory, new matter is continuously created as the universe expands, maintaining a constant density. Then there's the oscillating universe theory. This theory posits that the universe undergoes a series of expansions and contractions. After expanding to a certain point, it contracts back to a singular state, only to expand again. This cycle repeats indefinitely. Another fascinating idea is the multiverse theory. This theory suggests that our universe is just one of many universes that exist simultaneously. Each universe could have different physical laws and constants, making them unique. String theory also offers an intriguing perspective. It proposes that the fundamental particles we observe are not point-like dots, but rather tiny, vibrating strings. These strings' vibrations determine the particle's properties, and this theory could potentially unify all fundamental forces of nature. Lastly, there's the theory of cosmic inflation. This theory suggests that the universe underwent an extremely rapid expansion just fractions of a second after the Big Bang. This inflationary period smoothed out any irregularities, leading to the uniform universe we see today. Each of these theories offers a unique perspective on the universe's origin. While we may not have all the answers yet, the quest to understand where we come from continues to drive scientific discovery and exploration. And then there's cosmic inflation. Right after the Big Bang, the universe expanded faster than the speed of light. This rapid growth smoothed out any irregularities, making the universe look pretty much the same in every direction. The cosmic inflation theory, proposed by physicist Alan Guth in 1980, suggests that the universe underwent an exponential expansion in the first tiny fraction of a second after the Big Bang. This period of rapid expansion lasted for just a minuscule fraction of a second, but it had profound implications for the structure and evolution of the universe. During this brief period, the universe expanded by a factor of at least 10 circumflex 26 times its original size. This means that what was once a subatomic particle-sized region ballooned to a macroscopic scale in an instant. One of the key predictions of the cosmic inflation theory is the uniformity of the cosmic microwave background, CMB radiation. The CMB is the afterglow of the Big Bang, and it provides a snapshot of the universe when it was just 380,000 years old. Observations of the CMB reveal that it is remarkably uniform, with only tiny fluctuations in temperature. These fluctuations are exactly what the inflationary model predicts. Without inflation, we would expect to see much larger variations in the CMB. Another prediction of the cosmic inflation theory is the existence of quantum fluctuations. During inflation, tiny quantum fluctuations were stretched to macroscopic scales, seeding the formation of galaxies and large-scale structures in the universe. These quantum fluctuations are believed to be the seeds from which all the structure in the universe grew. Without inflation, the universe would be a much more chaotic and uneven place. The evidence supporting the cosmic inflation theory comes from various observations, including the detailed measurements of the CMB by satellites like COBE, WMAP, and Planck. These observations have provided strong support for the theory, showing that the universe is flat, homogeneous, and isotropic on large scales. The Planck satellite, in particular, has provided the most precise measurements of the CMB to date, further confirming the predictions of the inflationary model. The data from Planck has shown that the universe is indeed flat, and that the initial conditions predicted by inflation match the observed data. In summary, the cosmic inflation theory not only explains the uniformity and structure of the universe, but also provides a framework for understanding the initial conditions that led to the formation of galaxies and other cosmic structures. It remains one of the most compelling and well-supported theories in cosmology today. So, what was before the Big Bang? That's a tough one. The Big Bang theory suggests that our universe began as a singularity, a point of infinite density and temperature. But what about before that? This question has puzzled scientists and philosophers alike for decades. Some scientists think our universe is just one of many in a multiverse. The multiverse theory proposes that there are potentially infinite universes, each with its own set of physical laws and constants. These universes could be parallel to ours, existing in higher dimensions or even in different phases of time. One popular idea is the bubble universe theory, where our universe is just one bubble in a vast cosmic foam of universes. Each bubble could have different properties, and some might even have different dimensions of space and time. Another intriguing concept is the quantum multiverse, which arises from the many worlds interpretation of quantum mechanics. According to this theory, every quantum event spawns a new universe, leading to a branching tree of realities where every possible outcome occurs. There's also the mathematical multiverse, which suggests that all possible mathematical structures exist as their own separate universes. In this view, our universe is just one of many that can be described by different mathematical frameworks. The landscape multiverse theory, rooted in string theory, posits that there are a vast number of possible vacuum states in the universe, each corresponding to a different set of physical laws. Our universe is just one of these many possible states. Others suggest time itself started with the Big Bang, so there was no before. In this view, asking what happened before the Big Bang is like asking what's north of the North Pole. It's a question that doesn't make sense within our current understanding of time and space. It's like asking what's north of the North Pole. The concept of before the Big Bang might be meaningless if time itself began with the Big Bang. This idea challenges our understanding of causality and the nature of existence. The implications of the multiverse are profound. If multiple universes exist, it could mean that every possible history and future is realized somewhere. This could have significant implications for our understanding of reality, free will, and the nature of existence itself. While the multiverse remains a theoretical concept, it pushes the boundaries of our imagination and challenges us to think beyond the confines of our own universe. It opens up a realm of possibilities that could redefine our place in the cosmos. As scientists continue to explore these ideas, the multiverse remains one of the most fascinating and controversial topics in modern cosmology. Whether or not we ever find evidence for other universes, the quest to understand the multiverse will undoubtedly lead to new insights about our own universe and the nature of reality. The journey to unravel the mysteries of the multiverse is just beginning. As we look to the stars and beyond, we are reminded of the vastness and complexity of the cosmos and the endless possibilities that lie within it. But let's delve a little deeper into these theories. Quantum fluctuations are all about the weird and wonderful world of quantum mechanics. At the smallest scales, particles are constantly popping in and out of existence. These tiny random fluctuations might have been enough to trigger the Big Bang. Imagine that like this: the vacuum of space isn't empty, it is a seething sea of particles and antiparticles appearing and disappearing in an instant. One of these fluctuations might have provided the spark for our universe. To understand this better, we need to dive into the concept of quantum fields. These fields permeate all of space, and particles are essentially extensions of these fields. Quantum field theory describes how these fields interact and how particles are created and annihilated. The Heisenberg uncertainty principle plays a crucial role here. It states that we cannot precisely know both the position and momentum of the particle simultaneously. This inherent uncertainty leads to fluctuations in the quantum fields, causing particles to appear and disappear. In the early universe, these fluctuations were incredibly significant. The energy from these fluctuations could have driven the rapid expansion known as inflation. During inflation, the universe expanded exponentially, smoothing out any irregularities and setting the stage for the formation of galaxies and other structures. Evidence of these early fluctuations can be seen in the cosmic microwave background radiation to the afterglow of the Big Bang. These tiny quantum fluctuations eventually grew into the larger scale structures we see in the universe today. So from the smallest scales of quantum mechanics to the vastness of the cosmos, quantum fluctuations have played a pivotal role in shaping our universe. And that's the fascinating journey of quantum fluctuations, from the mysterious depths of quantum mechanics to the birth of everything we know. Next, let's talk about cosmic inflation. This theory, proposed by physicist Alan Guth, suggests that a fraction of a second after the Big Bang, the universe expanded exponentially. This rapid expansion stretched out any initial irregularities and made the universe appear uniform. Picture a balloon with tiny wrinkles. If you blow it up really fast, those wrinkles smooth out, and the balloon looks uniform. This process also helps explain why distant parts of the universe look so similar to each other. The cosmic microwave background radiation, often referred to as the afterglow of the Big Bang, provides strong evidence for this theory. Scientists have studied this radiation in great detail, and the uniformity observed supports the idea of cosmic inflation. During this rapid expansion, tiny quantum fluctuations were stretched to macroscopic scales. These fluctuations eventually led to the formation of galaxies and large-scale structures in the universe. Computer simulations show how these initial fluctuations evolved over billions of years. The distribution of dark matter also aligns with the predictions made by the inflationary model. Researchers continue to refine the theory, exploring its implications and seeking new evidence. Some extensions of the inflationary model even suggest the possibility of a multiverse, where our universe is just one of many. This idea, while speculative, opens up fascinating possibilities about the nature of reality. As we continue to observe the universe with more advanced telescopes, we hope to uncover more clues about the inflationary period. New space missions are being planned to gather more data and test the predictions of cosmic inflation. Understanding cosmic inflation is crucial for piecing together the history of the universe from its earliest moments. It helps us comprehend how the universe evolved from a hot, dense state to the vast cosmos we see today. The Big Bang marks the beginning, but cosmic inflation explains the rapid expansion that followed. By studying this period, we gain insights into the fundamental forces and particles that shaped our universe. The quest to understand cosmic inflation continues, driving scientific discovery and expanding our knowledge of the cosmos. Now you might be wondering, if the universe is expanding, what is it expanding into? The answer is it's not expanding into anything. Space itself is expanding. Think of raisins in a rising loaf of bread. As the dough, space expands, the raisins, galaxies, move away from each other, but there's no edge or outside to the bread. The concept of an expanding universe was first proposed by Edwin Hubble in 1929. He observed that galaxies are moving away from us in all directions. This observation was based on the redshift of light from distant galaxies. Redshift occurs because the wavelength of light stretches as the universe expands. This discovery led to the Big Bang theory, which suggests the universe began from a single point. Since then, the universe has been expanding continuously. Evidence for this expansion also comes from the cosmic microwave background radiation. This radiation is the afterglow of the Big Bang, providing a snapshot of the early universe. But what drives this expansion? Scientists believe it's due to a mysterious force called dark energy. Dark energy makes up about 68% of the universe and is pushing galaxies apart at an accelerating rate. So, what does the future hold? If the expansion continues, galaxies will drift further apart. Eventually, distant galaxies may become so far away that they are no longer visible from Earth. This could lead to a cold, dark, and isolated universe in the far future. However, there are still many unknowns, and scientists are continually studying to understand more. The expanding universe remains one of the most fascinating and profound discoveries in cosmology. And about that multiverse idea, if our universe is just one of many, it opens up a whole new set of possibilities. Each universe could have different laws of physics, different histories, and even different dimensions. It's like our universe is one bubble in a vast, frothy sea of bubbles. Finally, let's touch on the concept of time. Time as we know it started with the Big Bang. Before that, the concept of before loses its meaning. It's like asking what happened before time started. Some scientists theorize that the laws of physics as we know them break down as we approach the Big Bang, making it a boundary beyond which we can't see. Now, let's delve deeper into the nature of time itself. Time is often considered the fourth dimension, alongside the three spatial dimensions. In the context of the multiverse, time could behave very differently in each universe. Imagine a universe where time flows backward, or one where time loops in a never-ending cycle. These are not just science fiction ideas, but are grounded in theoretical physics. The concept of time travel also comes into play. Wormholes, theoretical passages through spacetime, could potentially allow for travel between different points in time and even different universes. Einstein's theory of general relativity provides a framework for understanding how time can be warped by gravity. Near massive objects, time slows down, a phenomenon known as time dilation. In the vicinity of a black hole, time could slow down to such an extent that it almost comes to a halt. This extreme warping of time could have fascinating implications for the multiverse. Parallel universes might exist in layers, each with its own timeline. These timelines could intersect or diverge, creating a complex web of temporal possibilities. Quantum mechanics also introduces the idea of superposition, where particles can exist in multiple states at once. This could mean that different timelines are not just theoretical but could be happening simultaneously. Scientists are still grappling with these concepts, trying to understand the true nature of time and its role in the multiverse. The answers could redefine our understanding of reality itself. As our universe continues to expand, so does our quest for knowledge. The mysteries of time and the multiverse are far from being fully understood, but each discovery brings us one step closer. The journey to unravel these cosmic mysteries is ongoing, and who knows what we might discover next. The concept of time and the multiverse is a fascinating frontier, full of endless possibilities. If you enjoyed this journey through the origins of the universe, we have so much more in store for you. The cosmos is vast and full of mysteries waiting to be unraveled. Don't forget to like, subscribe, and hit that bell icon so you never miss an episode of Cosmic Wonders. By subscribing, you join a community of curious minds and space enthusiasts. Drop your questions in the comments below, whether it's about black holes, the Big Bang, or the possibility of extraterrestrial life. We love hearing from you, and your questions fuel our exploration. Engage with us and other viewers in the comments. Share your thoughts, theories, and discoveries. Your participation makes this journey even more exciting. Until next time, keep looking up and stay curious. The universe is a never-ending source of wonder and inspiration. Remember, every star you see in the night sky has a story, and every question you ask brings us closer to understanding our place in the cosmos. Whether you're an amateur astronomer or just someone who loves to gaze at the stars, there's always something new to discover. From the latest space missions to groundbreaking discoveries, we cover it all. Stay tuned for more exciting content that will take you on a journey through space and time. We'll explore cosmic phenomena, delve into the mysteries of dark matter and dark energy, and keep you updated on the latest astronomical events. Our channel also dives into the history of space exploration, celebrating the milestones and achievements that have brought us to where we are today. And we look forward to the future, anticipating the next big leaps in our quest to understand the universe. Join our community of space enthusiasts, and let's explore the universe together. Your curiosity and passion drive us to keep creating and sharing. As Carl Sagan once said, "Somewhere, something incredible is waiting to be known. Let's find it together." Thank you for watching Cosmic Wonders. Until next time, keep looking up and stay curious.